Good morning, good afternoon, everyone, and welcome to the Permian Tech Talk session. My name is Yora Nawawi, a graduating senior majoring in petroleum and energy engineering at the American University in Cairo, and it's a pleasure to be your moderator for today's session. We're excited to have Seth Anderle, strategic business manager at Halliburton Drill Bits, with us today to present on how to minimize well time and maximize drilling directional performance. Seth brings over 10 years of experience in drill bit technology, design and application, focusing on both fixed cutter and roller cone drill bits. He has contributed to advancements in drilling performance and risk mitigation through innovative technology applications. He's also an MBA graduate from Sam Houston State University, which complements his technical knowledge with his strong business insight. And today, Seth will be sharing his insights on the latest drill bit technology and how these innovations are reshaping drilling operations in the industry. Please join me in welcoming Seth Anderle and as he presents his expertise on the latest developments in drill bit technology and its impact on the future of the drilling operations. And if you have any questions, please leave them in the Q&A box and I will read them out for you at the end of the session. Seth, please take it away.
All right, good afternoon, and thank you, Yara, for the introduction, and thanks to PioPetro for including us in this tech talk. So today's session, we're going to focus on an industry trend around short shank or shankless type bits. And as you can see, the title of the presentation is How Do We Minimize Well Time for Our Customers Through Maximization or Maximizing Directional Performance. So I'd like to get started with a little bit of the challenges and why short shank bits or shankless bits have entered the market. So if we look at the industry in general, we are seeing higher dogleg severity curves in order to maximize lateral length for a given field or area or specifically lease line. So the tighter you can build your curve, the more lateral length you can get out of a lease line. So maybe historically, if you were looking at building on 4 to 5 degrees per 100, you're giving up production length because your lateral has to be shorter. The second is the move to longer laterals in the industry. So I was part of the Permian Technology organization for Halliburton about 5-ish years ago. And at the time, folks were drilling 1-mile laterals was kind of the standard, and they were evaluating 2-mile laterals. Today in the Permian Basin, it seems like nearly every operator has standardized on about a 2-mile lateral, with some operators drilling 3 and even 4-mile laterals in the Permian Basin today. So why? Well, you get longer lateral length for drilling to increase your production on your lease lines. And finally, the kind of last industry challenge that we're trying to address with these shankless or short shank bits is safety, specifically safety from reducing trips. So pipe handling, tripping is one of the biggest safety risks that occurs on a drilling rig. And if we can keep our bits in the ground longer, if we can combine sections, if we can combine a curve and a lateral or a vertical curve and a lateral, we can reduce the safety hazards from tripping and pipe handling, as well as save rig days for our customers. So if we kind of look about it from an operational impact and really kind of what are we trying to do here? There's been a shift in the industry to more and more rotary steerable systems. And one of the reasons for this is the ability of rotary steerables today because of their increased reliability. And they can now drill curve and laterals in a single run and vertical curve and laterals in a single run. But they do present unique challenges for drill bits. So historically, if you're going to drill a curve and a lateral, you might go in with a conventional motor assembly with a 2.12 degree bend. You have a highly steerable bit. You go knock out the curve, you trip, then you go in with a different bit, slightly different design parameters to go drill the lateral. And the reason behind that was when drilling the curve, you need a very, very steerable drill bit. You want to build angle, you want to cut to the side very effectively and efficiently. However, once you get into that lateral or even in the vertical, your goal isn't just steerability anymore. Your goal is stability. So you want to maintain a stable bit for borehole reasons, but you also want to maintain a stable bit for vibrations and potential tool failures from having high vibes at your bit. And so, how do you combine those two things to work in a single run for rotary steerables? Well, historically, that was very challenging because rotary steerables could only build at, let's call it 5 to 8 or 6 to 8 degrees per 100. Well, the directional industry, they started using flex assemblies. So they knew that it was a challenge to hit their 10-degree build target or more. So they had put this very flexible assembly in their BHA that allowed it to build at a higher rate. So they could achieve their 10 degrees per 100 or even 12 and 13 degrees per 100. However, when that assembly got into the lateral, it was very limber. And any movement or any push of formation on the bit would make that assembly steer. So you would see big swings in inclination and azimuth due to the flexibility of that joint in the BHA. And so the industry was like, how do we solve this problem? Well, one of the ways to solve that problem is to have a more steerable bit. So instead of having to add the flex joint, you could just put a more steerable bit on there, knock out your curve, be stable in your lateral, to combine those sections, to combine the vertical curves and laterals, to combine the curve and lateral into a single bit run. And in essence, that is what our Hypersteer product line does. That is the trend that you're seeing in the industry for shankless or shorter shanked bits. So let's dive into a little bit of detail for you guys who haven't been 20 plus years in the bit industry on why we have a shank in the first place. So let's clear up some terminology here. This gray piece right here below the bit head and above the API connection is what the bit industry terms as a shank. And you can see the standard here, short here, and now our Hypersteer, it's virtually gone. And so when I talk about a standard bit, this is how the industry built bits 10 plus years ago. And the reason why is because we had to have a weld joint. So the bit head, if it was made out of matrix, which is a tungsten carbide infiltrated material, not very friendly to welding. So you can't just slap on a connection here. You've got to do something different. So the industry would put a blank assembly, another steel assembly inside, and then we would weld on the API connection. So one of the reasons why you couldn't do this all in the same operation is because you have to melt a binder material to create your bit head. Well, that means you have to get a furnace up to, let's approximate it at 2,000 degrees. What happens to steel at 2,000 degrees? Most steels become virtually annealed and they lose their strength. So you can't just go put steel in a furnace, infiltrate your bit head, and then go make it up to a rotary steerable or a motor or a bit box and expect it to last. So the industry found that creating your bit head and then welding on a high strength material for connecting to your BHA was the way to go. And so that was the standard for a really long time. The next iteration in trying to reduce length was twofold. You could build the bit out of solid steel, and then you could leave these breaker slots here so that you could make the bit up to the BHA, or you could put your weld inside of that breaker slot. And so now you had the option to build a steel body in a shorter configuration or a matrix body in a shorter configuration. And again, I want to highlight these slots right here. Their only purpose is to allow torque to be applied to the bit to screw it on to your BHA. Again, whether it's a rotary steerable, a motor, or a bit box. So that's where we were, and where are we today? So today we're at the Hypersteer configuration, and as you can see here, relative to a standard bit from just a handful of years ago, on average, we are producing bits that are about 44% shorter. That's specifically on our slim hole bits. So if you call it 6 3/4 hole size and under. And the way that we accomplished that was by building a bit completely out of steel and moving this breaker slot to the gauge pads. So now you can get your cutting elements here on the edge, your cutters, really close to the directional tool. Again, whether it's the pads on a rotary steerable or the bend on your motor. So that is kind of the progression and how the industry has moved over time. Now let's get into what are the actual benefits. How does making a shorter bit help the industry? So when we look at bits and BHAs, particularly on rotary steerables, we worked with our Halliburton directional company, Sperry, on modeling DLS sensitivity, only changing bit length. And what we found that has been proven in operations is that on a slim hole bit, so a 6 3/4 inch size bit, if you can remove approximately 2 inches of length, you can increase your dogleg severity by 1.5 degrees to 2 degrees on average. So what does that do for us? Why is that important? Well, you kind of heard my statement earlier on historically what rotary steerables can build at. If you're sitting at an 8-degree build with a rotary steerable, but the operator needs to hit 10s in order to maximize his lateral length for his lease, what options do you have? In the past, it was add a flex joint, which will get you your 10s, but you're probably going to trip in the lateral because the bit's walking all over the place. Or you can go to a shankless hypersteer style bit, improve your DLS by 1.5 degrees to 2 degrees, and now drill that curve and lateral in a single run. So I've got an image on the next page kind of talking about why we want to get those bits, or why we want to get the bit closer to the kick pads on a rotary steerable. So if you look at the left image here, this is a rotary steerable assembly. It's an iCruise from Halliburton. Here's the kick pad. What happens is these pads will kick, they will push off of the formation and direct the bit in the well. So if the pads kick this way, it's going to push the bit down. If the pads kick this way, it's going to push the bit up. But what is the physics of what's happening there? When it pushes off, the cutters are what actually causes the bit to drill sideways. It's not the gauge pad. It's not this empty space. It is these cutters. And we call these gauge and lower shoulder cutters. And we want as much force getting into these cutters as possible in order to maximize steerability. So there are things we can do from the design perspective to make these cutters a little bit more aggressive while maintaining durability. But what we kind of missed was all of this empty space here. So as you push here, there is some deflection. Yes, it looks short, and yes, this is all steel, so it is stiff, but there's just a little bit of deflection. And so the closer you can get these cutters to your kick pads, the more force that's transferred from the kick pads to the cutters, allowing the bit to be more steerable. And that's what we're showing on this right image here. The kick pads are here. We brought these cutters much closer. And so essentially what we did was we eliminated this dead or wasted space between the kick pads on a rotary steerable and our gauge cutters on our PDC drill bits, allowing us to achieve that on average 1.5 degrees to 2 degree more dogleg severity when run on the end of a rotary steerable tool. Okay, but there are some other benefits. So I mentioned earlier, when you're in the lateral, your main focus isn't necessarily steerability. Now, if the operator is geosteering or something happens and you need to change course, yes, the bit still has to be able to steer. But stability and managing vibrations is huge once that bit gets into the lateral. And I've got a trend on the screen here. Again, this is very simplistic, but I'll show an example later on how this works in practice. That gauge length is correlated to hole spiral. So the longer your gauge, on average, the less borehole spiral you're going to have. The shorter the gauge, on average, the more hole spiral you're going to have. As your hole begins to spiral, you get vibration. Those two things are also correlated. So if we want to minimize vibration and minimize hole spiral, one of the levers that the bit industry can pull is gauge length. But that is in direct opposition to steerability. What's great about shankless drill bits, specifically our hypersteer line, is that you can now do both. You can reduce your total makeup length by going to shankless hypersteer. And in many cases, you can increase your gauge length while still being shorter than the reference design. So there are still some operators out there who don't run hypersteer for these applications, but they require the very, very short bits. So one example might be, hey, I want to run a standard bit, but I need the makeup length to be at 5.5 inches or less. Well, how do we as a bit company accomplish that? Or how does any bit company accomplish that? It is to eliminate your gauge pads. We know that eliminating gauge pads can have a negative effect on both stability, so vibrations, and borehole spiral. So by moving to hypersteer, you can get the best of both of those, shorter bits with longer gauge pads. And I want to talk a little bit about the graph in the bottom right now. So some of you might think, well, how do you prove that? How do you prove borehole spiral without running some expensive tool in the ground to do borehole imaging? Well, we worked with a customer a couple of years ago, and they had a pretty clever idea. They wanted to test the difference between a bit that had a 4-inch gauge and a bit that had a 6-inch gauge. While drilling, both of them drilled roughly the same ROP. They both completed a 2-mile lateral in a single bit run. And so there wasn't a lot from the runs themselves that you would go, oh man, this bit was way better than the other one. However, they started recording hook load when they were running casing. And what they identified is that the bit that utilized the 6-inch gauge pad had more available hook load when casing got to TD than the borehole that had the 4-inch gauge pad. And so let's break this down a little bit. If you have more hook load less, so in this case on the screen, the right image is showing 140,000 pounds of hook load. The left image, you're getting down to about 100 to 120,000 pounds of hook load left. So why is that? Well, it's friction. And what causes friction? Borehole spiral. So if you can minimize the borehole spiral, you have less friction while running your casing, leading to more hook load left when casing hits TD. So this was kind of it was a fun exercise, but it was a relatively simple way to qualify friction in your wellbore, which is directly correlated to borehole spiral or ledging or other events that would not cause your borehole to be straight. So while yes, the graph on the left, spiral to gauge length, it's kind of just like an industry known without a lot of data behind it. This is a way that this is a relatively simple way in operations to go verify, justify, prove if you're better or worse from a borehole spiral standpoint. Okay, now that I've kind of explained a little bit about what hypersteer is, I've got a short video and I'll walk you through it just to kind of better visualize what's occurring, how we're building these hypersteer product lines. Okay, so this is the traditional bit on the end of a rotary steerable. We are effectively eliminating the shank, and then we're adding those breaker slots back into the bit head. And again, the whole point of doing that is to get those cutting elements on the bit as close as possible to the steering head, and more specifically, to the kick pads on the rotary steerable tools. Okay, so the bit design is one thing, how we're building the bit, how we're making it shorter, but in the end, it's a system. The bit has to work with the BHA, and we need confidence that that bit that is selected is going to work on the first try. We don't want to be guessing on, does this bit work with this BHA? Does this bit work with this rotary steerable tool? We don't want to have to prematurely trip because we didn't get our build rates. And historically, the industry has used a term called side cutting efficiency, or SCE. It is a high level parameter of a drill bit that tells you how steerable that bit is. And it's a pretty simple calculation. It's just the axial aggressiveness of a bit. So how fast does it want to drill ahead versus its lateral efficiency, or how fast does it want to drill to the side. It's a simple ratio. It's a good estimation of how the bit will perform, but it's an estimation. It doesn't get into the unique details of cutter position, cutter back rake, cutter chamfer, gauge pad taper, gauge pad length, bit length. There was a lot left to be desired. It worked pretty well, but it was not bulletproof. We would still have issues where couldn't get the build rate, and we wonder why, because the SCE matched our minimums and we still struggle. And so about a year ago, we launched what we're calling our bit tilt or bit tilt capability simulation. In this simulation, we are taking the bit and the BHA separately. We're looking at, if you apply a side force to the bit, how much does that bit want to tilt off of its axis relative to the rotary steerable tool or the borehole. So it's a pretty simple calculation, but we're taking everything into account. We're taking the profile, the cutters, the backup elements, the gauge pads, the length. Everything is being taken into account. But that's only half the story. The other half is the BHA. And so again, we've worked with our directional company at Halliburton, and they are now simulating their BHA. What forces can be output from the BHA, and what dogleg capabilities they need from those side forces. The beauty of bit tilt is that it can be used in the design phase, during pre-job planning, and as a drilling optimization tool. And I'll give you some examples on the next slide. So here's what I like to call bit tilt in action. Here is a curve, just a generic curve that we created to show how this works. But it combines the bit plus the BHA. And so I'll do just a quick summary here. The red line is the tilt angle of the bit at a given side force under a low depth of cut. So again, for those of you who aren't long-time bit people, depth of cut is simply the depth the bit travels in a single revolution. It is directly correlated to ROP. I'll give you the calculation on the next slide if you want to dig in. The green curve is what the bit will tilt at a given side force for a high depth of cut. So what you'll notice is that as your depth of cut increases, the tilt of the bit decreases. But that's just the bit. We still have to have the BHA component. And so that's what these red and green dashed and dotted lines are. It is what the BHA requires of the bit in order to achieve a given dogleg severity. And so, well, quick example, if the dashed and dot curves are under the solid line, we have high confidence that you're going to meet your dogleg objectives. If your dashed and dot lines are above the solid lines, you will not achieve your dogleg objective. So in this particular case, let's say we wanted to drill at 9 degrees per 100. So red, again, is low depth of cut. If we want to drill at 9 degrees per 100 at low depth of cut, we have margin, right? This dot is below our curve. We can achieve that. The bit and the BHA will reliably produce 9 degrees per 100 with this much tilt margin, if you will. However, if you want to achieve 9 degrees at a high depth of cut, it's not going to happen. The bit can only produce about 0.45 degrees of tilt at this given side force, but the BHA needs it to produce over 0.6 degrees of tilt in order to achieve a 9-degree dogleg. So again, from a planning standpoint, we look at this pre-job and we know exactly where we need to be from a parameter standpoint to hit our targets. Or maybe we need to redesign our BHA and redesign our bit to make sure that we have enough margin to hit our targets. The other thing about this is you can use it while drilling. So let's say you're trying to hit your 8, but you're at a high depth of cut and you're like, man, why is this system not delivering the dogleg severity that I require? What can I do? Well, let's see, if I drop depth of cut, does that help me? So I move to the red line. Oh, yes, it does. So it's a real-time parameter optimization. If I drop my depth of cut, I can now achieve my desired dogleg, and I don't have to trip this assembly for build rates. Here's a little bit more details on depth of cut and what we call our relief angle. They are both extremely impactful to our simulation and how we design our bits. Most bit guys will tell you they love to speak in depth of cut and not in ROP or weight on bit. It is how the bit is engaging with rock, and it is our #1 tool for analyzing a drill bit. On this right image, what I really like to highlight is the gauge area. So this is the gauge length. And then we can design this gauge to be relieved or stepped or relieved and stepped in order to achieve our given dogleg targets. The reason why we do that is our cutters, they actually want to fail rock. But this gauge pad, it's either steel or matrix. When it touches rock, it does not want to fail rock. It just rubs against rock. So if we start rubbing gauge pad, it prevents these cutters from digging into the drop rock and drilling laterally at its maximum potential. Okay, I'm going to turn it over to Emilio. He is our Permian Basin technology lead, and he's going to talk a little bit about how this technology is being used, not just in the Permian Basin, but in our global operations.
Thank you, Seth. I'd like to start this part just showing you all some statistics of what we have been doing so far with this technology, which is proven since this was released. So in the Permian Basin specifically, what we can see right here is like we have been drilling more than 3.1 million feet with this technology. Our success rate building curves and laterals in one single run is extremely high, over 96%. And we also have been proving that this technology can work on both RSS on conventional or motor type of drive. That part is very important because most of the applications nowadays is attached to RSS, but we have proved as well that there's some benefits by using this technology on conventional assemblies as well. As Seth just mentioned, there's some benefits on building curves with this. It should be easier. So at least on the Midland Basin right now, in our case, the fastest curve build on a slim hole size 6 3/4 is an 8 hours curve, which is good compared to what the hours or the curve hours used to be in the past with conventional or standard drill bits. He also mentioned some advantages on increasing gauge length without affecting the overall makeup length. That's for sure beneficial. So I'm highlighting that part right there. That also helps just to increase doglegs capabilities. And also from the field test that we have been doing, we have actually realized and identified that there is some benefits in terms of shocks and vibes when we use this type of technology. I think the fact that the bit is actually closer in this case, if we are talking about an RSS to the key packs, that helps with drilling dynamics and for sure there is some like advantages and good things that we can just take from this. Go to the next one, please. So this is a case study from Middle East. This is a good example. We use, or this case study is combined with Sperry iCruise RSS. On this one, we use exactly, I would say, the same drill bit crown or putting structure, and the one on the right is a standard PDC bit, and the one on the left, the red one, is a hypersteer. So the challenge right here was to complete the BCL in one single run. BCL means vertical curve and lateral in one single run. And the idea was reduce the drilling time. So the result proves, in this case, that we increase ROP by using the hypersteer technology by 30%. And this is key in this part, and I want to highlight that. The reason why they actually increase P rate or ROP on this one, if they were able just to increase the amount of weight on bit they were applying while building the curve. How is that? Basically, with the standard bit, considering the dog legs that they need to achieve just to build the curve the way that they want it, they have to control at some point weight on bit just to be able to build that curve. Since they start using the hypersteer technology and improve that cycle and efficiency with this, they didn't have to do that. So they built the curve at the higher ROP, achieving the doglegs that they were expecting, and that ended up in a better overall run with this new technology. The second one is a special case because this was also on iCruise RSS. This is a new tool that Sperry is releasing this half of the year. So we designed a specific bit for that tool. So the challenge right here was to complete, once again, on this case, 778 whole section, the curve and lateral in one single run. This was in Midland Basin. And the plan was to build the curve on tens. So the results prove that we did it in one single run as it was planned. The ROP was higher than expected, and we built on the way that it was planned. The final duel, bid was almost green, was 111 WT. So the process that we follow right here and kind of like aligning this with what Seth mentioned before, what we did was basically customize this design and start trying to collaborate with Sperry on this new tool size, just to guarantee that the bid would provide wax needed, right? So we started doing the simulations, the BTC calculations that he just showed before, just to guarantee that our bid design will build, especially the curve that the way that they wanted. So when we validate this at the test rig, we were able just to build the curve up to, 11 on the curve. In reality, we did it or build the curve on 10. And basically that was the way just to deliver a good performance, but there's a lot of homework and collaboration behind that. This is actually the post-run recap on that run. Just want to highlight, we drilled we drilled from 8,000 the curve and the depth was 27,000. So we drilled over 18,000 feet. With this, speed rate was close to 220 feet per hour. And duel, as you can see on the pictures, is really good after drilling the entire interval.
So I want to hit on what's next for this technology. Today, this type of technology is virtually only available in steel. And it goes back to that challenge that our industry has on matrix. We have to melt a binder material, it infiltrates a bit head, and that occurs again at roughly 2,000 degrees. Most steels come out soft, not able to be used to make up to a BHA. But there is a desire in the industry, to use matrix body drill bits in the hypersteer format. And so that is where we are moving. We have built a handful of bits that are matrix body in the hypersteer configuration, and we have started testing in the Permian Basin. What are some of the advantages of Matrix? Well, if you have a very abrasive application, yes, we do put hard facing on steel body bits, but we can start to see erosion. We can see erosion of the hard facing, we can see erosion of the base metal, and it does limit the life of our steel bodies. One thing that folks don't always think about, though, is the erosion on the inside of our drill bit. So with a matrix body drill bit, we're pulling everything so close to the rotary steerable that it's seeing higher and higher flow rates on the inside. Steel has a tendency to erode on the inside. Matrix bodies, because they have that tungsten carbide in them, will resist that internal erosion much better than steel. And finally, there are some advantages from the design perspective. So when we build a matrix body drill bit, we are designing a mold. Typically, those molds are made out of graphite. They're very easy to cut. We can manipulate geometry a little bit manually with clay and other displacement items. Whereas on a steel body bit, you have to have line of sight drilling or milling to create your steel body. So on average, we have a little bit more design flexibility from spacing, from erosion, from back rakes, side rakes, all of those things that go into making a high performing drill bit. And Emilio, I'm going to let you wrap up here with a little bit of a summary on where these bits have run and what they've done so far in the Permian.
Thank you. So good news is like we already start testing this new technology. This is a run that we have in Delaware Basin, drilling a Wolfgang A target formation. So this time was only a lateral run that we drilled with this technology, over 5,000 feet drill with this. As you can see there, there is some broken cutters, but the application was quite hard. But related to the bit body and the technology itself of the Matrix Hypersteer, there's no concerns at all. And results were great after this. We just keep running with this specific client in the Delaware Basin. Some of the runs that we don't have right here, but then results has been consistent. Then Seth just mentioned the advantages in terms of erosion, for instance. So when we drill a longer laterals, which is the case these days, drilling 3 miles, 4 mile laterals, erosion is always a concern when we use steel. So in this case, as you can see over there, there is non-erosion and no any signs of concerns on the body of this Matrix Hypersteer.
Okay, thank you so very much, Seth and Emilio, for that outstanding presentation. Your insights into drill bit technology and its applications have provided us with a deeper understanding of how innovation continues to drive drilling efficiency and reliability. We have some questions, though. The first question to you is, how do you use machine learning or predictive analytics to recommend bit types or parameters based on offset well data? Seth, we can't hear you. You're muted.
Can you hear me now?
Yep.
Yeah.
Okay. So we're doing a couple things on machine learning and prediction, if you will, of bit performance. So I'd like to highlight maybe 2 of them. The first is a technology that we have in-house, and it's called Oculus. It is our automated dull grading technology. So we use machine learning to grade each individual cutter on a drill bit. So for those of you familiar with IADC dull grading, you get an inner and an outer dull grade, and you have room for 2 types of dull characteristics. Those can range from broken tooth, worn tooth, chipped tooth, spalled tooth, delaminations, etc. But you're really just giving an average of the inner and the outer. Moreover, it is done by a human, and there is bias built into that. What person A says is a 1 wear flat, person B might say is a 2 wear flat. So our goal when developing Oculus was to take the bias out of the measurements. So we use images, then we apply machine learning to those images, and we dull grade not just inner outer, but we dual grade every single cutter for both severity and type. So that's the 1 through 8 dual grading for IDC, as well as worn tooth, chip tooth, etc. We then feed that back into our design process. So each designer has access to that, and they can look at the overall performance of the bit relative to its dull condition to make design changes. The other piece that we do is we have internal simulations that take all of this data. So it takes bit record data, if we have surface data, if we have a technology called Cerebro, whether it's Cerebro vibration or Cerebro force, we can feed that back into our design process to optimize design and performance for our customers.
Okay, now for the second question, how do you balance between bit aggressiveness and steerability to achieve both high ROP and accurate wellbore placement?
The simple answer is moving to hypersteer, but let me get a little more detailed. So steerability, there are several factors that affect steerability. One is bit length, kind of the point of the presentation today, but it's also how you design the shoulder and gauge cutters, as well as your gauge taper, gauge relief angle. Those are probably your biggest factors in steerability. And so obviously that has to be balanced with overall cutting structure aggressiveness for ROP. What I will say is that when you reduce length, you allow yourself to be more aggressive on the overall bit design and still deliver the dogleg severities that are required from our customers. So we do have our simulation tools. We not only simulate dogleg severity and build rate capability, we also simulate ROP performance through weight on bit and torque on bit simulations. So yes, I think the question had balance in there. That is absolutely correct. Every decision that we make as drill bit designers is a trade-off, but that is what our job is. We have to balance dogleg severity and cutting structure aggressiveness, but the hypersteer is a key feature that allows us to go more aggressive and still maintain our build rates.
Okay, perfect. The third question is, what is the approximate life of using hypersteer bits?
Oh, that is a challenging question. I guess the simple answer is it varies. So bit life is very dependent on the application. We have applications in North America and globally where we only average a run or two per bit before they are scrapped out or out of service. We have other applications where we can see 5, 6, 7, 8 runs per bit. But specifically when it relates to hypersteer, the life of a hypersteer bit is no different than the life of a standard steel body bit. So it's still the same materials. The gauge pads hold up just the same. We can still make and break bits the same. So on average, we don't see a delta between a standard steel body bit and a hypersteer drill bit.
Okay. And how does the hypersteer bit compare to the standard drill bit in terms of flexibility and performance in high temperature, high pressure wells?
So regarding high temperature and high pressure, there is no change. Our materials used in the bit industry, you have steel, you have tungsten carbide, you have carbide matrix powders. None of those are going to be anywhere near their limit in high temperature wells. The only component on a PEC drill bit that is going to be affected by high temperature is going to be the O-rings that we use to seal our nozzles in the bit. So there's no difference between a standard bit and a hypersteer bit when it comes to temperature limitations.
Okay, and is the technology still under pilot or is it implemented as a standard practice in Halliburton?
Great question. Hypersteer is a commercialized product for us. We commercialized in late 2023, and we are currently in testing with the Matrix version, which we hope to be ready for commercialization early to mid 2026.
Okay, perfect. And another question, and how do these optimized bid designs impact the overall drilling cost per foot and well delivery efficiency?
Great question. So our goal is a bit company, and likely most bit companies are going to say something about reducing well cost or reducing well time. In the end, it comes down to two things. How fast are you drilling and how long can you stay in the hole? So the faster you drill, the less cost per foot. Generally, the longer you drill at an acceptable ROP, the less cost per foot. So it is directly correlated. ROP and bit life or run length are absolutely 100% correlated directly to customer cost to deliver a well.
Okay, and another question is how do Halliburton's fixed cutter and roller code drill bits compare in performance across different reservoir types, and how do you decide which to use in a specific scenario?
Oh, I love that question. So at Halliburton, we have a process that we call DACI, or Design at the Customer Interface. And essentially what that is we place our application engineers and our design engineers in the basins where the activity is occurring. So let's take Midland Basin or Permian Basin, for example. Emilio, he sits in Midland. He's our technology lead. He's a bit designer. He's an application engineer. His job, his role is to be an expert in our customers' applications and to select and or design bits that are meant to succeed, meant to perform in those specific applications. And so that's how we approach it as Halliburton. We don't go out and build a whole bunch of bits and then try to go run them. We evaluate customer needs, formation, rock type, BHAs, fluids, and then we recommend a solution to meet those needs.
Okay. With hypersteel directional bits, how do the latest material innovations help improve the performance in deep water drilling or extended reach wells, where stability and precision are critical?
Yes. Okay. So whether it's deep water or extended reach or unconventional or conventional applications, materials have come a long way in the drill bit industry. None more than PDC cutter technology. So if you were to take a snapshot in time of cutter performance today relative to 5 years ago, 10 years ago, 20, it really doesn't matter. Pick a point in history. The performance of those cutters is outstanding today versus any time in history. From an abrasion standpoint, they last longer. From an impact standpoint, they don't damage as quickly. And so the gains in cutter technology have been absolutely huge for the drill bit industry. But that's not the only place where we've seen material performance increases. When we look at things like hard facing, you can't really run a steel body downhole. It's going to erode, it's going to abrade, you're going to lose a cutter. So what the industry has done is use a tungsten carbide hard facing material that we apply selectively to locations of the bit. The step change in how, not just how it's applied, but the base materials and their erosion resistance and their abrasion resistance has just been fantastic. We are now running steel body bits in applications that in the past we would have never thought possible due to the advantages of the hard facing. There's also just base steel technology and machining technology that is helping the bit industry become more efficient and building stronger, more durable bits overall.
That's great. And another question, with the rise of AI-driven drilling systems, where do you see the role of hypersteel bits in the future of automated drilling? Do you think these bits will be able to self-adjust based on downhole conditions?
So absolutely, I believe hypersteer will be a key piece as we move into more automated drilling. AI is such a buzzword, and I bet every company, drill bit or oilfield services or oilfield company, exploration companies are all looking into AI. We all have projects around it. What I can say is I believe that all of these tools, once they come together, will drastically improve efficiency, but that's not going to change the base material requirements of bits or other elements in the BHA. So while yes, we are all looking at AI and how that's going to help drilling efficiency, we can't get lost in AI only. We still have to do the core development for bits, which in general is going to be cutters, body materials, and design/simulation tools.
Okay. The last question is, in terms of performance tracking, how does the real-time data from hypersteel bits compare to historical benchmarks, and what improvements have been made in data accuracy and predictive analytics for future drilling campaigns?
Gotcha. So that's a big question. There's a lot that goes into data collection, how accurate that data is. I'm going to be a little bit high level on this one, but in general, we have the ability to capture data at the bit now. So we have tools, Cerebro and Cerebro Force, that can capture weight on bit, torque on bit, rotation at bit, and vibration at bit in 3 axes at the bit itself. Historically, those measurements have been anywhere from, let's call it 3 to 5 foot on a rotary steerable or more, up to 20 or 30 foot on a conventional BHA assembly. So those insights have been incredibly impactful to understanding the dynamics of a downhole bit. If we take maybe a step up and look at just drilling in general, there are several companies out there that are looking at drilling automation tools. I know we are as a company, Halliburton's looking at that, but we're looking at full automation, not having to send data to surface to have a human make a decision, but utilizing a combination of downhole data with surface data that is processed and sends commands while drilling to automatically update parameters for improved drilling efficiency.
Okay, perfect. Thank you so much again, Seth and Emilio, for your outstanding presentation. I'm sure our attendees have gained deeper understanding of the innovations shaping the future of drilling operations. And on behalf of everyone involved, I thank you, and we look forward to the continued conversations and innovations in the Permian Basin and beyond. Have a wonderful rest of the day.